I hope you're all doing very well this evening, and I hope you're all here to listen to what our graduate, John Grotzinger, has to tell us a little bit about Mars. So, Dr. Grotzinger has come here in a spirit of generosity. When he visited a couple of years ago, you know, I have to say, this is an honest quote. It's like, I am so impressed with this work you guys are doing with your students and with the students at this place. Can I come back, right? And we're like, yeah. So that's why he's here. And certainly he's an eminence in the field. And he's a graduate of the geoscience department, yay for us, in '79, and went on to do many interesting things. But one of the things you've probably heard of him doing is being involved in various kinds of the Mars missions, including for a while being the lead scientist for Mars Science Laboratory or Curiosity mission. So he has graciously offered to tell us a little bit about that mission, as well as kind of what we're thinking about for the one that's going to launch in next July. Super exciting. So that's what I want to say. We are grateful for his time, and he's come to be with you all, right? And so I'm really grateful for that. And please tell us what you'd like to about Mars.
Well, thanks very much, David.
Yeah, no worries.
You know, it's a pleasure to be here, and I had a fun day meeting with some of you guys and finding about what you're interested in, what you want to do, and so I thought that I would share what we're doing on the mission, and okay, yeah, wow, it's angry at me. And so I thought what I would do is I'm going to keep this low pitched because I see some kids in the audience, and you know, you guys are our future for all this stuff. If we want to have these space missions and we want people to do science, people need to get inspired about what we're doing. So I'm gonna skip a lot of the science we're doing because it's come along well. Rover's been going on for about 8 years now. It'll be its 8th year this summer. And there was a lot of science discoveries, but now because of that, the next one's going to launch this summer. And there's a lot of cool technology associated with these missions, so I'm actually going to focus on that. And so if you're interested in engineering and mechanics, we're probably going to talk about that more than science, but it comes along with a lot of cool stuff. So the backdrop here shows where Curiosity is right now, just coming out of the shadows of the base of this mountain. This mountain is 5 kilometers high, and it sits in this huge crater that's about 140 kilometers wide. That's about as big as the footprint of the big island of Hawaii. And so we chose this site for a bunch of reasons that I'll talk a little bit about in a minute, but not too much. But before I get into that, I wanted to thank all the people that work on the team. This was the mission team at the time we landed. There's about 200 engineers here that I worked with every day for about 6 years up at the Jet Propulsion Laboratory. And then connected to this group that was doing operations in California were 500 scientists distributed all over the world, 13 countries, dominantly US, but 13 countries, depending on who contributed an instrument to the rover payload. This is the most complicated vehicle that mankind has ever built. It's so complicated that not one person can understand all the subsystems. If something goes wrong, it's always decision by committee until we get to the very top, and then eventually a single person usually makes the final decision. But this is really systems engineering at its greatest, because this is not something that anybody had ever built before. So when you make one of these things, you do it exactly one time. Now, a great exception is about to happen with that this summer when we launch a facsimile of Curiosity. Right now this rover is called 2020, which is the year it will launch. NASA had a competition. Probably any day in the news you will hear about the name of this next rover. But the idea is to save the taxpayers money by building more or less the same thing And then at the front of the rover, it's all folded up here. We have a drill that we use to drill holes on the rocks in Mars. Then we put the powders into the rover, and I'll talk more about that later. But the next one is, instead of drilling, it's going to have a coring bit, and it will collect samples of rocks to bring back to Earth. So you can look forward to whether or not that thing will launch successfully and then land successfully. So I'm going to spend some time talking about the launch and landing that I haven't done for a few years. So this is fun for me too, to kind of go down memory lane with all this. Why are we doing this? It's about this question of life on Mars. And this has become a really refined question as a result of the last 50 years of missions to Mars. So we don't think there's any higher life forms on Mars. We actually don't think there's life on Mars because there's no evidence for life on Mars. But we have a hypothesis that maybe the earliest history of Mars could have been the kind of place where these little microorganisms could have survived. But then, because Mars is actually very different than Earth in some ways, it lost its atmosphere, the whole planet changed, it remains in a state of sort of suspended animation, but there could have been life evolving on Mars that left microorganisms. So that's the search. That's what's going to happen this summer when they launch this rover that will go up, collect the rock samples, and if you guys saw The Martian, it's the same mission architecture. You have to have a Mars ascent vehicle go down to Mars. It has to have a little rover go out and collect the samples that the next rover will collect. And then it has to shoot them back up into the atmosphere. They go into orbit around Mars. And then when Congress releases more money, some decades from now, those samples will come back to Earth. But in the meantime, this is what we imagine. Science begins with imagination. You have to have an idea that becomes a hypothesis, and then you have to execute a plan to investigate that hypothesis. So this is our idea, that early on in the history of Mars, there was water. Probably not as much water as Earth, probably not big oceans, but there could have been lakes and shallow seas that might have been very extensive. And this is an extreme environment on Earth today. It's very salty. It can become very cold. It gets dried out. But despite that, microorganisms can live there. So the key ingredients for life as we know it, number one is water. So we've known this now for decades, that on Mars it once had water, fairly substantial amounts. The goal of curiosity was to analyze the rocks and find out whether or not that water had the right components in it that would be the key chemical ingredients for life. So it's one thing to show that there was water, there's another thing to show what the chemistry of that water was. And then based on that, you can sort of use your biology to figure out whether or not there would have been energy for metabolism. So I'll talk more about that later. But let me step back and talk about the history of the exploration of Mars, because this is fun. So back around 1910, 1915, there was an astronomer, an amateur astronomer called Percival Lowell. And Lowell had a telescope that he built in Flagstaff, Arizona, 12-inch telescope, that he would look up at Mars, and this is a map that he made, and it even got to be quite popular on this pack of cigarettes that you see here. I'm not quite sure why that was, but they went with it. And what Lowell imagined, he could recognize that there were ice caps on the poles of Mars, and he imagined that he was seeing canals. And these canals must have been built by intelligent beings that were desperate because of climate change. And this is, I'm not making this up. The idea is that Mars was drying out, and they had to build these canals to ferry water from the poles to these dark spots, which he thought were oases, where people had grown and aggregated and populated to escape termination. So that idea floated around for a while, and then that hypothesis was tested when Mariner 4 flew by Mars in 1965. Here's what it saw. There were no canals. There was no water. There wasn't anything that looked like anything on Earth. It looked like the moon. But you've got this highly pixelated grayscale image that was kind of a marvel of computer science at the time. And science didn't really feel good about Mars anymore. So what happened was a couple of other missions went by. There was a very important one. In 1969, a mission called Mariner 9 flew past Mars, a different part of Mars, and there were none of those craters in Moonlight's surface, and instead there were these things that looked like all these dendritic branching channels. And a big discussion started in the science community. Were these channels cut by water? One person would say that. And the next person would say, Mars is really cold. How do you know it wasn't liquid CO2? Another person would say, Mars is really cold. How do you know it wasn't liquid nitrogen? So just because you see evidence of what looked like a fluid flowing across the surface of Mars doesn't necessarily mean it was water. There was a fourth idea, which was maybe it's just an artifact of the imaging system and it doesn't really exist. Okay, so 1975, the year that I entered Hobart as a freshman, the Mariner mission went into orbit and it looked at exactly the same terrain and it confirmed that hypothesis 4, that it could be an artifact, was out. There is no question these are not artifacts, and if anything, it actually looks better than it did before, and now you can see all these meandering patterns as well. But the question still remained about whether or not that fluid that cut that rock was water or not. Okay, so then you go forward a couple of decades, and then there was another seminal mission, another orbiter, now with this glorious camera that had very high resolution, and it takes a picture of a place called Walde crater, where there was a river channel that ran in, and it made this thing that just looks like a river delta. This thing is so confidently a delta that the science community often will just call it the Walde Delta. Here's what this means. You look at these channels and you see that as they anastomose around, they build up on top of each other. They're not just going back and forth at the same level. At the same time they're going back and forth, they're also rising up in elevation. The only way you get that is if there's a standing body of water there. So this was the first time. This made the cover of something called Science Magazine, which is a big deal if you're a scientist. And it was a convincing argument that there should have been standing water on Mars. So then NASA, based on that, decided to create rovers that would go across the surface of Mars. And that's when I first got involved. I was on my first sabbatical. I was actually living in the Sultanate of Oman. And a friend of mine, a paleontologist at Harvard, said, John, you should submit a proposal to get on this mission. And I kind of laughed and I said, well, how do I work on this in Oman? And plus, what am I going to do if we land and we find all these volcanic rocks, which is what Mars was supposed to be made of? So anyway, it landed in 2004 and changed my career because it turned out it wasn't lava. It was kind of rock that forms in the presence of water and also wind. And this is what we saw. It just looks like you're looking at a very small version of the side of the Grand Canyon or some place where there's layered rocks. And the cool thing about this was you can see that some of these layers are dipping relative to the white line. Everything above the white line is parallel to the white line. Everything below it is dipping. So there's a whole story behind that I'm going to skip. But this was compelling because at the same time, we could also analyze the chemistry of these rocks, and we found out, and the mineralogy, and we found out that in those minerals, they had bound water. So you'd get a mineral formula that had a bunch of symbols, and then it would have H2O. We proved that. And so based on that, then NASA said, now you get to go ahead for the next decade and build Curiosity. Let's sample those rocks and find out exactly what the chemistry of this ancient environment was like. So here we go. We picked this place in Gale Crater. This is the landing ellipse, which allows us to have the rover land in a relatively flat place that is safe, and then wander over to the foothills of this mountain where from orbit we see the same kind of layering but at a really big scale. Whenever we see this layering, we get excited. And the reason for that is if you look into the Grand Canyon, these layers that you see here sitting one on top of the other, guys, this is like reading a book, okay? The first chapter's down here, and the second chapter's here, and the third chapter's here, and as you turn back the pages of the history of the Earth, you find out about the story of the Earth. And so this is what we wanted to do for Mars. So we chose Gale Crater because it had a really thick stack of layers, and we're going to start at the bottom and go upward. Now, we're never going to go to the top. We can't do that. The rover's going to die. The hills get too too steep. We're not going to make it, but at least we're going to get that first installment and find out about the oldest history of Mars, which is the part when we think there was water there. That's the part we're most interested in. Okay, so you get this idea as a scientist, but now you have to execute it and test your hypotheses. You need instruments. You got to make measurements. So in our case, we needed rovers. So you might have noticed in those pictures I showed of Mars that there was a big gap between when I entered Hobart and when we found the delta, like as in 25 years. And part of the reason for that was that in the 70s, they also had a lander go down, the Viking lander, and it had a life detection experiment on it. So NASA decided to swing for the fence. If there's life there, we're going to look for it. And so it had experiments where the lander would reach out, scoop up some soil, add some water, and then if there were microbes in there, metabolism would occur, and there'd be gases that would betray the fact that life was there doing its thing. And it didn't work. And there were two of these landers. The mission cost $1 billion in 1975 dollars. That's expensive. And so Congress said, you guys failed, you're done. And so that's the reason for that big gap. So the science community retreated, thought hard about it, came up with this better hypothesis that the earlier history of Mars is the better part of Mars. Problem with Viking, it was sampling and looking for life in modern Mars. That's not good. That's what we learned. So we went to ancient rocks. So that's part A. Part B was any geologist that's looking for fossils needs to know they need to walk around at different places. You can turn over this stone, and it's got nothing in it, and turn over this one, there's nothing in it, and then you get this one, and magically there's fossils there. So finding the good stuff sometimes takes just luck, but you can increase your chances for luck by having a mobile vehicle. So you don't just land and look around, you actually move around. So the idea here was to build a rover, and what you can see here, the design calls for a 6-wheel rocker bogie suspension system. And in English, what that means is that the rover can move over an obstacle, like a rock, the same diameter as the wheel itself, without tilting the deck of the rover, which is paved with solar panels. So if you're a solar-powered vehicle and you tilt away from the sun, that's not good. So that's the reason for the development of this suspension. So this thing was launched on the 4th of July in 1997. And it was called a technology demonstration. It was not a mission. And so NASA covers themselves that if this thing fails, it's not mission failure. This is for real. It's a tech demo. And if the demo doesn't work, then that's not a problem necessarily. But it worked. It operated longer than its lifetime. It's longer than it's sort of a warranty. Every rover comes with a warranty, and after that, it's all bets are off. And so it went ahead to the next decade. In 2004, we got Spirit and Opportunity. I already showed some of the stuff that Opportunity found. But what you can see is the heritage. Heritage really counts a lot here. You got the same 6-wheel rocker bogie suspension. You got solar panels up here that are huge relative to the energy demand, because what this rover taught us is that there's dust settling out of the atmosphere all the time. And that dust settles on the solar panels and it diminishes the energy flux that the solar cells produce. So the way that you mitigate that risk, because maybe this thing operated in a time when the rate of dust accretion was lower on Mars. What happens if you land that thing at a time when the dust accretion is higher? So you mitigate that risk by making bigger surface area. You don't use windshield wipers, that's what some people ask me, because that's another mechanism. And you want to avoid mechanisms that have moving parts. That's not the way to go when you're building these things if you can avoid it. The biggest difference is that you can see that the cameras are up on top of the rover here, and that means this thing is a ship which leaves its port when it lands, and it goes sailing around looking for good stuff. Whereas this one was tethered to the ship that landed on Mars, and it could never get away from an area about the size of this table up here. So this was very successful. We found minerals that had water in their structure, And then that gave rise to Curiosity. And again, you can see the pedigree here, 6-wheel, rocker bogie suspension, cameras up on top. It's got this enormous arm out in front, which has the drill rig on it, where we can drill down to 7 centimeters total depth. And then inside the belly of the rover is a very sophisticated suite of instruments, including things that do X-ray diffraction and mass spectrometry. And so we can drill a rock sample, turn this thing up over our shoulder, and dump the rock sample through a hatch in the top of the rover, and it goes down into the belly of the rover and gets analyzed. The biggest difference that you can see between these two rovers and this one is this one's got no solar panels. And that's because there is a sleeve in the back here where we stick in the very last thing that happens at Cape Canaveral. If it's a human mission, the humans go in, they shut the hatch, and off they go. In our case, we drop in a plutonium-238 source, which is wrapped with a thermocouple. It's called a radioelectric thermoelectric generator, which is NASA code for nuclear power. And that way we can operate the rover at night, which is really important because all these instruments work best if they work when they're really cold at night. So that power source is about 100 watts per hour. So based on 100 watts per hour, we can operate this whole system if we figure out how to efficiently do things. Okay, so why did it work? You know the real estate thing, location, location, location. Well, up at JPL, we have the same expression. It says, test as you fly, fly as you test. So we never build anything that can't be tested, and then once it gets to where it's going, we never do anything with it that can't be tested. And what this engineer is doing is she's got a wand, and at the end of the wand, there's a little temperature sensor, and she's touching it into the rover, which is being bathed in sunlight, which has the same intensity that the sun gives Mars. So this is a very realistic potential heat source. And we're seeing the way that the rover responds thermally to this temperature to see how well the measurements that she's making with this agree with what the computer predicts. Because this is systems engineering. We can test every part individually, but we don't know how the whole thing is going to work until we stick the whole thing into a test bed and give it a run. And then we can compare it to the models and figure out where the problems might be. Temperature turns out to be really important because this thing's all metal. Some of it's copper, some of it's titanium, some of it's aluminum. They all stretch at different rates, and so stuff can break. And so almost all spacecraft failure, which is not the result of an explosion on the launch pad or a crash on landing, is the result of thermal cycles that eventually cause a wire to break. So we'd like to avoid that. So we do a lot of testing. If it doesn't work, you don't launch it. And that's the deal. Okay, so here we are down at Cape Canaveral, which was in 2011. This is the night before Thanksgiving. And we're going to launch the next day. It turned out we had a little glitch with one of the batteries, so we postponed one day and launched on Black Friday instead. And everybody else is out shopping, and we're launching rockets. And so Curiosity's up here at the top. This is the standard kind of a launch configuration. And what I'm going to do now is show you a video of what happens when the rover lands, and to try to set this up a little bit because it's kind of fun. The guy who made this video had worked at JPL for 25 years, making the same kind of standard videos. But when he took this challenge on, he didn't really talk to his manager. He kind of went below the radar and interviewed all the engineers. All the people you see here are the people who made all the key decisions. There's a little film noir. You'll see he's got some shady angles going on here. And this thing generated a lot of tension. It's hugely instructive. It's very accurate, so much so that NASA didn't want us to release this thing. And so I had to make a few trips. Other people had to go visit. And eventually, they decided to release it. The thing is, if we would have crashed, they would have said, we look like idiots because these guys said we were. And then, but when you don't, people go, well, this is just great. So the same thing is going to happen about a year from now. On February 17th, 2021 is going to be the next one of these events. So I'll just set that up and let you guys watch it.
when people look at it, it looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering thought, but it still looks crazy. From the top of the atmosphere down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive and dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror, because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0 in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from gravity. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag. Our heat shield, it heats up and it glows like the surface of the sun. 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow, constrained space. This is one of the biggest challenges that we're facing, and one that we have never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck-snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it'll only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we've got to cut it off and then come down in rockets. Once we turn those rocket motors on, if we don't do something, we're just going to smack right back into the parachute. So the first thing we do is make this really radical divert. We fly off to the side.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land. And we head straight down to the bottom of the crater, right beside a 6-kilometer climb run.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms and it could damage instruments. So the way we solve that problem is by using the sky crane.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long, and then gently deposit on its wheels on the surface.
As the rover touches down and is now on the ground, the descent stage is in a collision course with the rover. We must cut the bridle immediately and fly the descent stage to a safe distance from the rover.
So it worked. Otherwise, I wouldn't be here. And so that video is called 7 Minutes of Terror. You can find it on YouTube, and you can also find other ones where, after it was done, we spliced in, remade it, but spliced in actual footage from the landing itself. So I'm just going to show you a couple of still images to show you how we choreograph the monitoring of something like this, so that if it does go wrong, we get some more information back from it. So, for example, the image on the left shows the parachute fully deployed. It's taken by a orbiter with a camera on it called HiRISE. And so we can sync these things down to extreme precision so that we know in the sequence when Steve Lee, the greatest understatement, if everything doesn't work perfectly, the rest of the sequence won't work. That means crash. And so our biggest fear, the biggest risk, as Anita Samgupta was saying in the video, was the parachute testing. Parachute testing was critical. This is the largest parachute ever made. It has to be deployed at Mach 2, and it has to inflate immediately and be successful. What was happening in testing was something the engineers call squidding. It was flopping back and forth like this. It was inflating and then deflating, inflating and deflating. And so what this picture was designed to do, HiRISE took 2 pictures. I'm not going to show you the second one. It doesn't look any different than the first one. But it was designed to see whether or not the parachute was squidding. And so what you see here is perfect deployment. This is hard to get right because we actually don't know what the atmosphere structure, we don't know what the structure of the atmosphere is on Mars. It's dense in some layers, less dense in others, and all that feeds back to the behavior of the parachute. But this is really a good picture, so that gives us information. It's not just cool public outreach, it actually gives us data. And then this is a picture that was taken the next day after the landing had happened, and it shows the back shell still attached. There's a bridle here that you can't really see, but then the parachute is collapsed, and that just simply shows us hardware on the ground. But there is value in that because you want to see when these things hit how much debris they generate. Okay, here's another one. So again, Steve Lee says, we got to get the heat shield off. It's like a lens cover that covers the camera. So there are 6 radar beams. They're pencil beams. They're very narrow, highly accurate. And when the heat shield comes off, the rover has an auto-seek command so that the radar seeks the ground and it starts obtaining information on the geometry of the ground. It feeds it back to the computer, which tells it to actually fly out of rough terrain if it's headed towards a cliff or sharp rocks or something like that. But what's cool about this is one of my favorite images of the mission because it shows the backside of the heat shield, which has successfully separated. So again, what would have happened is if the heat shield didn't separate, the camera would be taking pictures, but they would be dark because no light was able to penetrate in there. And there's a whole bunch of other information that would have come out. So then the next one is going to be an animated GIF. And what you're going to see is the heat shield hitting the ground here. So it's just going to kind of loop through. Watch out, there it goes. So it'll come back again. It'll just loop through here a couple of times. You can sort of see the heat shield flying just before you see the moment of impact there. You can see the heat shield, a little bit of a shadow, and then the splash it makes when it hits the ground. Can you guys see that? Yeah. So, I mean, it's amazing. You can download this. This is also on YouTube. The entire, from the minute that the heat shield separates, the descent camera turns on, and it makes a HD movie of the flight all the way down to the bottom, including this. So I just took one frame out of the movie. This is the resolution that you get if you want to watch it. And remember Anita saying about how we had to develop the sky crane because the rocket propulsion system, if you come all the way down to the ground with the rockets, that force is so great, it will just throw debris all over. As you'll see in a minute, it threw debris around anyway, but maybe not quite as much. And there was fear that small rocks like this might actually eject and then hit the rover and break stuff. So we had to worry about that. But remember that because I'm going to show you a picture from orbit of the holes that did get drilled in the ground. Okay, then shortly after we land is the great moment for the team. So if you're at the landing, if you're listening to it, this will all be broadcast when it actually happens. Shortly after it lands, the engineers get all these semaphore tones that tell them that everything worked perfectly. And then you see everybody jumping up and down, and it's euphoric, and people are hugging and crying and laughing and having a great time. Now, when that happens, all the data that the engineers get is a result of a wrestling match that I lost with the lead engineer to get some data back to show the public that we actually landed. But what the engineers want is as much data as they can get to tell them about spacecraft state of health. Obviously, that's much more important to know about. And so the way this works is that they set up the landing so that Earth is on the horizon, and as we land, we have an antenna that can actually send, at a pretty slow data rate, information to Earth. That's what the engineers want right away. But in that very low bandwidth connection, I was able to sneak in this image on the left. One black and white grayscale image that basically shows, if you look carefully, you can just see the corner of the wheel on the ground, but you can see the shadow of the rover. You can see all the schmutz that accumulated on the lens cover for the hazard avoidance camera. That's what took this picture. The front of the rover has 2 hazard avoidance cameras. The rear of the rover has 2 hazard avoidance cameras, and I'll show you how we use them later. But in the background, we had a big discussion about what this halo was that we were seeing here. Was it the mountain that we had come to explore? That's a very emotional moment for the science team because that's what we're trying to do. So then what happens is Earth sets on the horizon, the engineers get all the data, there's an initial assessment, and then as that's happening, the same orbiter that took the picture of the parachute has gone around Mars and is coming back again to get more information, but we can also send information from the rover to the orbiter, which then ricochets it back to Earth in what's called a bent pipe transmission. And so now what you can see here is, yeah, that's our mountain, and it's a good one. And now you can definitely see the wheel. You can see the second wheel here. And the great thing about it is you can see the shadow of the rover increased by 39 minutes, closer to sunset. So this is really cool. So what happens now is that's all the data the science team gets, but that's a lot of data. You cannot imagine 500 scientists that have been waiting almost 10 years to start looking and measuring the sizes of these pebbles and talking about all the processes that are going on there. People are speculating about the mountain, but we landed at 10:30 p.m. Pacific time. And what happens is we have to operate during the Martian day. And the problem with that is the Martian day, Mars rotates once every 24 hours and 39 minutes. And so ever so slightly, we come back in and out of phase with the Earth. It's like getting in an airplane and flying 2/3 of a time zone westward every day. And then you do it again, and you do it again. And then eventually, we go to work 39 minutes later. We get off work 39 minutes later. We eat dinner 39 minutes later. You're having beers at Conrad's at 5 o'clock in the morning because you just got off work. And stuff like that. We did this for 5 months. And the reason why is because it gives us the most time to plan the activities of the rover as thoughtfully as possible. So I told the team, I said, okay, you guys, let's just ditch the feeding frenzy for the time being because we won't have any more data tomorrow. So let's go to bed and get rested up and ready to go. So everybody goes to bed, we come back the next day, and here's what we saw. What we saw was taxpayers having fun. And this is really good because nobody's going to make any money off of this. But the rover did cost $2.5 billion, and we would like the people who paid for it to enjoy it. And I can't tell you how much great stuff we've got. There was a few things I put in, and then I actually took one out because I'm not sure how good it is anymore. But people love to look at this data. I know somebody, a guy up at the University of California at San Francisco, who probably is the person that gets the credit for solving the riddle of the SARS virus. He and his lab group of molecular biologists come to work every day and download our data and try to figure it out for us. They're not geologists, but every once in a while they hit pay dirt and they send us something and they say, have you seen this? And I and others say no, and then we wind up doing it because they saw something good. So the data does eventually come. And so this was one of the great moments where the camera does a 360-degree panorama. But it's huge data volume, so it takes forever to come back to Earth. But as it comes down, this scene is amazing because this is the first time anybody has ever seen a vista of Mars with anything other than this stuff down in the bottom. Gravel, rocks, looks gray, looks bleak. But now you see mountains, and there's like some bedrock in the foreground here, which is exactly what we came for. It looks layered. And for those of us that live in LA and drive out to the desert, looks like a little LA smog coming in here, there's haze. It kind of looks like home. It's not that weird anymore. The strange planet just seems a lot more familiar. So we wait and wait and wait, and then eventually the really good data comes down at the highest fidelity. And here's our mountain. And this is my favorite picture of the whole mission. It's hard to imagine what it's like to look down at a planetary surface for almost a decade, and then one day you're there. And now you're looking up at it, and that's a big mountain. And so all we have to do is drive 12 kilometers. That was the downside of this landing site, by the way. There were other choices where we landed right in the good stuff. We didn't need to drive at all. But this one was just inescapable for field geologists because all field geologists like to walk around. And then when you get up in the mountains, you can see all the layering here. So this is what we're after. This is our history book. This is chapter number 1 down here, and 2 and 3 and 4. And then we get up here, something different happens. We're probably never going to make it up there. Right now, we have just gone around this hill over here after 7 years. Here's our map. I'll just show this quickly. We landed here at Bradbury. Ray Bradbury was a science fiction writer who died shortly before we landed, so NASA named it after him. And we were supposed to head over here. This dark stuff that you see, these are all sand dunes. We would have loved to have just driven this way, but we couldn't. So depending on exactly where we landed, here, 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 or here, we always had to go around these dunes. We knew that was a risk. We had to take it. There's a risk that the wheels might break before we even got to the promised land, but so be it. And so now we've made it up here to the Vera Rubin Ridge, which is named after Vera Rubin, who was a famous astrophysicist, and she died recently, and the team named it after her. And this is an amazingly interesting place. It has basically brought together all of our observations, and if the rover died tomorrow, nobody would regret it. But we're going to keep moving. And so the plan is for the next year, we're going to come up. There's a valley here, and we hope by the time Curiosity really slows down, we should be up to this violet-colored unit here. But I need to tell you the story of why we didn't just start driving this way. I had told the media, I had told NASA headquarters that our goal when we picked this landing site was to get outside of this yellow line as quickly as we could. That's the landing ellipse. And as I said, the biggest risk would be to land in the center of the landing ellipse, which is 20 kilometers, and you have to drive 10 kilometers before you even get to anything that begins to look interesting. But there's a lesson about science and serendipity, and we were talking about it at the intro geology class today. I'm not going to go into it, but we chose to drive more or less in the opposite direction to go look at some rocks that from orbit, after we studied them, they began to look really interesting. And so the science team begins to develop energy to do something very different, but it requires us to drive in the opposite direction. So I go back to NASA headquarters and I tell everybody why we want to do this different thing. And they say, but John, isn't that adding risk to the mission? I say, yes, it is, but it could pay off. And it did. So here's how it worked. So here you can see Curiosity. This is about 3 days after we landed. This is a false color image. So this camera that's orbiting has 3 channels in it. And we've tuned the data so that it shows all the features the best. But Curiosity is painted white. And so what we do is we just take the image and we threshold it so that those pixels get saturated, and then that enhances the area that was disturbed when the rocket thrusters were blowing all that dust around. So this is basically a map of the outline of where the ground was disturbed during the landing. The butterfly wings that you see here are where Anita Semgupta said there's going to be a bunch of stuff flying around, and there was. This is actually bare rock either side here. We would have loved to have studied it, but it's probably been contaminated by the propulsion gases. So we decided to move on. And then here's the reason we went in the opposite direction. The science team mapped 3 types of terrain, and you don't have to be a geologist to get this. Here's the smooth, hummocky terrain. Here's the cratered terrain. And then here's the light-toned, fractured terrain. Anybody can do that. The important thing is 1, 2, 3 of them come together in this point. And for a geologist, that's just irresistible. Because if we drive to that point, not only do we sample this unit, but we can get this one and this one in close proximity. So it's like getting a threefer. For a small amount of risk that I explained to NASA, instead of the actual distance, I just said, look, it's 5 football fields. And they said, oh, that sounds fine. And on the way to the press briefing, I knew I was going to have to explain this to the media because they wanted to know why we were going the opposite direction. So I said to the science team, we have a list of 100 names that we have to choose for this location. They get pre-programmed into the rover, and then we use them, and then we send up another group of names. So I said, somebody please pick a name. And about 15 minutes later, I get an email from a graduate student that said, the team picked this name, Glenelg, which is actually a rock formation in Canada that's named after a town in Scotland. But the important thing about it is it's a palindrome. So this was genius. So what this means is that we're both coming and going, that we are going to leave. We're not planning to spend a bunch of time there. We want to go have a look, and we're going to get going. As you'll see, we wound up spending 1.5 years there, and it was really a gold mine of stuff. So, okay, so for the kids, let me tell you guys how we drive this rover. It's 300 million miles away from Earth, so we can't joystick it because there's this thing called the speed of light. So, you know, we can't really, we would like to be able to do this, but we can't really. So here's how we do it on Earth. We write an app for our smartphones, and we actually do it this way. This is the lead engineer commanding Curiosity's equivalent. This is a rover that has none of the brains, but it has the same mass and it has a big heart, and so we call it Scarecrow. And we drive this thing around and we practice everything we're going to do on Mars, we do it on Earth, but we do it driving using a cell phone, because when you press the button here, the distance in terms of how long it takes and the speed of light is really short. So it goes to the rover right away, and the rover knows exactly what to do. But the problem is on Mars is that we have this time delay. So Mars is currently about 300 million miles away. It takes the speed of light at that distance about 17 minutes to get there. So if the rover is going along the ground and it gets to a cliff, and you tell it to stop, it's already been off the cliff for 17 minutes. So that doesn't really work well. So instead, what we do is we talk to it twice a day. When the sun rises on Mars, we send a signal from Earth, no matter what time it is on Earth, and that's the hard part. No matter what time it is on Earth, we tell the rover to wake up and do A, B, C, and D. And then, just after the sun sets on Mars, the rover sends a signal back to Earth, and it says, I did A and B, I didn't do C, and maybe I did D, but you're going to have to go look at the error anomalies to try to figure out whether that happened or not. So this is why we live on Mars time, because we have to do it when the sun rises on Mars and when it sets on Mars. So you kind of wind up living like a vampire for part of the time. Okay, so here's also how we drive, and a little bit more information. So this was our first drive. So this is amazing. This is one of these deeply emotional moments, especially for the engineers. This is like watching your child take their first step. So here's where we landed. Okay, we have 17 cameras, but none of them are under the belly of the rover, so we can't really take pictures of this. So there's no information here, but the other cameras are looking out. And so all these pictures that you see here are the cameras looking out. But we have to use specially calibrated cameras, and some of them are down low in the rover. And so in this part, there are rocks here. There's a rock here, 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 here. So all these brown patches that you see are shadows. There's no information. And if there's no information, there could be dragons. So nobody is going to drive over here when the coast is clear over here. That's rule number one. We do a blind drive. Everybody in the room agrees that if we drive this way, there are no dragons there, and we're going to go for it. But then at some point, you get to the limit of that knowledge, and then you have to go into what's called auto-nav. And I'm not going to explain that, but this is us simulating the first drive we're going to do on Earth up in the test bed at JPL with the Scarecrow, and we arrange and put objects out that look exactly like the map that we've made up here, and then we drive it. And we make sure we know exactly what the vehicle is going to do before we do that drive, because it would be an unmitigated disaster if in the first drive it broke down. That wouldn't look very good. Okay, so here it is. Here's actually the drive. So once we get all that information and we've tested it out, we then simulate it. Whoops, should have been going along here, but I guess it's not. So that's what it looks like. So basically what we're going to do is drive forward, and then we're going to do a turn in place. The front wheels go this way, the rear wheels go this way, and we do a circle, kind of like a pirouette. And then here's after we did it. So this is, again, one of these amazing pictures. This is where Curiosity landed. There is no vestige of a beginning. Turn a little play on words there. So we landed, and suddenly there are wheels and there are tracks. This is where the rocket boosters blew the hole in the ground, 4 boosters. We drove forward, just like we planned to do. We did a turn in place and then backed up and took a picture of the landing site. No great science, but a huge moment for engineering. Okay, so then we got on with the science. People gradually get their confidence, they feel more free with the vehicle, and you start to do more stuff. So this is a terrain where we wanted to drill our first hole, and the idea was to find a target that the geologists like and get on with it. So as we were moving in that direction, we discovered interesting rocks. And again, you kind of don't have to be a geologist. This is really good. You see this rock, it looks like a piece of concrete that somebody jackhammered up on the sidewalk. It's got pebbles in it. And on Earth, it's analogous to a rock that we call conglomerate, which is made out of pebbles. And it turns out that on both planets, this kind of a process is what gives rise to those rounded pebbles. You have rivers that flow along, they transport rock fragments, the rock fragments bang into each other, they get rounded up, and you get these rounded pebbles. So we found an ancient riverbed, which was a really good sign that we were going in the right direction, because what we'd like to find is a lake bed, and you just got to go with the flow, literally. So once we knew how the river was flowing, we went downhill. So it's no great surprise that here we're uphill, this is downhill, this is the riverbed, and we're going to go down in there and see what we find. Okay, so here's our rock. We got down in there. The science team looked at it. They saw that it was fractured and filled in with light tone minerals. You can see all these specks here that make it look like it's got the chicken pox. These are things that geologists call concretions, which always form in water. It just looked really good. So we drilled it. And here's what you get. This is the pinnacle of human civilization. For $2.5 billion, you send a rover to Mars and drill a hole that deep. That's the science we're doing. But the amazing thing about it is you see these fractures extend down to the rock. You see where we zapped it with our laser to get a sense of what the composition was like before we did more sophisticated analyses to get a sense of what was there. Long story made short, this thing was deposited in an ancient lake bed. Okay, now bear with me a little bit, guys. We're going to do a little bit more sophisticated science here. It won't get too bad, just a list of numbers. So these are minerals, and these are the kind of minerals, these top 4 that you see here, that make up the island of Hawaii. And Rock Nest was a soil sample that I didn't show you. We scooped up some soil first, you walk before you run. And these are the abundances that we saw there. And then here's the drill hole named after an engineer. And what you can see is all these abundances go down. And that's really important because as these abundances go down, this thing over here called smectite, which is a clay mineral, kind of like the stuff you build out of, it goes way up. It goes from 0 to way up. That's really important. And this one down here, this is an iron oxide mineral, but not all of the iron is fully oxidized. And it also goes from a very low abundance to a quite high abundance. So this was kind of a home run for us. Everything that we were hoping to do in building this rover was going to the direction of, can we find minerals that basically reflect the composition of rocks that form in the middle of, well, not the middle of the Earth, but the edge of the Earth, and could they be altered in water to form this kind of clay mineral? So with that, we got really excited, and now, this is as technical as it's going to get, we take another sample and we stick it into this thing we call the sample manipulation system, which has a bunch of quartz cups, and we drop the sample into a cup. The cup goes into an oven where we heat it up to almost 1,000 degrees centigrade, and it generates gas. The rock volatilizes, and as it's burning, we collect it, and we can pass it into all these instruments, and those of you that know what these are will know what we did, and everybody else doesn't have to worry about it. So here's what we did. There's just one graph. This is the only graph I'm going to show you all night long. So this is temperature down here. This is a lower temperature, this is a higher temperature, and this is the signal, the intensity of the signal the instrument's measuring. So as we start to heat this rock up, guys, what you got to think about is a cake baking on a cold winter day. You've been outside, you walk into the kitchen, and your glasses steam up. You know why they steam up? Because there's a lot of water vapor in the atmosphere. So what's happening here is that these black dots are the water vapor coming off of the cake. And the other thing that's happening is carbon dioxide, you know, the baking soda that you put in a cake, that's what it's doing. It's producing CO2, making the bubbles in the cake, and sometimes it gets released, so we're measuring that. And I'm going to stop with the metaphor there because it breaks down. But the important thing is that as we heat it up, we get two forms of sulfur. This is sulfate and sulfide. So they're in two different oxidation states. That turns out to be really important for the kinds of microorganisms that live without sunlight. That was a key finding here. And the last thing I want to point out here is when you get up around 700 degrees centigrade, as the water is dropping down again, it increases transiently. That's really important. That water is the water that's bound into the chemical structure of the clay mineral. So in a clay mineral, you get a layer of silicon, and then you get a layer of waters, and then you get a layer of other cations back to the water. You got to heat it up to get that water out. We did all kinds of stuff with that water. We measured its isotope ratio, kind of looks halfway between modern Mars and modern Earth, and it tells us the history of the drying out of this planet, but it was still wet at this time. Okay, here's the last thing. Scoop up the soil, drill the first hole, drill the second hole, drill the third hole. This happened about 2 months later. This happened 2 weeks later. This happened almost 2 years later. What happened was we were looking for this stuff. This is a very simple organic molecule. We found nothing. We drilled the hole. We found nothing. We adjusted all our parameters and found a better place with a whole bunch of these things called concretions. And then we found a lot of this stuff above the background, which was meaningful. We couldn't be sure it wasn't contamination, so we waited 2 years until we could drill a rock that, based on its depositional environment, as an ancient sand dune, we thought it should have none of this stuff, and indeed it was below the background again. So then we published our paper on that, and we found organic compounds on Mars. We don't know much about their origin, but it was very important because these are reduced molecules. Mars is oxidizing, and that gives us hope that if you go to a better place and return the rocks to Earth, we might actually find more sophisticated compounds. If you didn't understand any of that, here it's just pictures. When we landed the Opportunity rover, we didn't have a drill, but we had a scraper. And with that scraper, we ground the rock down, and we found out not only is the planet red when you look at it from Earth because of all the red dust that covers the rock, it was also red in its interior, which means all the iron is oxidized, which is not a great thing if you're a microorganism. When we drilled the spot that we found with Curiosity, based on a more sophisticated understanding of Mars, we found out that the surface of Mars, yes, it's still red, but beneath that surface it's gray, and the reason it's gray is because not all the iron is oxidized. So this is like going out to one of these basins that you see that build the brownstones from which the rock comes. For the brownstones in Boston, the brownstones in New York, and Washington, D.C., they all come from the same type of basin. And the reason the brownstones are brown is because all the iron is oxidized. But the rock that's also there that people use to build highways, because it doesn't look so pretty because it's gray, the iron is not completely oxidized. So this situation down here is a more favorable one for microorganisms that are trying to do metabolism based on chemistry. So let's talk about red earth. So this is a place just across the border between Portugal and Spain called Rio Tinto. And the Rio is Tinto because iron is dissolved in the water because the water is so acidic. This water has pH 1. And what can happen there is iron in the +3 state is actually soluble. And normally iron is not soluble in that water. So this is a big problem for microorganisms, but they still live there. Even though you've got this very low pH, they still live there. But the problem is when this dries out and gets really salty, they can't grow there anymore. It's not enough water activity. Here's what we found with Curiosity. You just have to ignore the higher grasses. We don't think we found any of those on Mars. But these are lakes that are often dry in South Australia. And all these rocks around here are the same kind of rocks that you have in Australia. And often it's wet, but sometimes it's dry, but it doesn't matter. And if you go there when it's dry, you dig below the surface, it's still wet. And earth is gray because all the iron is actually reduced here. And there's a whole bunch of microorganisms that live in there by harvesting chemical energy using exactly the same materials that we see on Mars. So a lot of the gray stuff in here is this iron magnesium smectite, the same thing that we found on Mars. So here it is. If you remember nothing else, this is what we found on Mars. With Opportunity, we found honey, and with Curiosity, we found batteries. So this is honey. We found water on Earth. Woohoo! Nature paper. You know, life on Earth because of the water. But the problem is there's not enough water. The reason the honey doesn't spoil on your shelf is the water activity is so low that microorganisms can't grow in it. So that actually wasn't a great environment that we found back in 2004. But the one we found with Curiosity, for the same reason a battery works, it's a solid substance that stores chemical energy. You hook the wires up, you put a light bulb in between, and it glows. And that's what a microorganism can do if you find iron in the +2 and the +3 state, sulfur in its different valences as well. And so we think we actually found a habitable environment. Now that doesn't mean that life originated on Mars. It just means that if it did, it had a good place to grow. Okay, I could show a whole bunch of other results. I'm not. I'm going to get back to the fun stuff. So we published this paper, get our picture on the cover of the Rolling Stone. Everything's great. John flies up to San Francisco to go to the big annual meeting that a lot of earth scientists go to announce all this stuff. We had a big press release, all that. It just couldn't get any better. And here's how life works. Literally, the minute I got out of the press briefing, I looked at my phone, I had a message from the chief engineer, please come back to JPL, there's a problem. So here's the problem. Our wheels were getting destroyed. So these are metal wheels, and they were made light, and they were designed to be light because when that landing is happening and the rover's dangling down on the kind of the rover on the rope deal just before it lands, you really want to make sure the rover's light. It's easier to control. So notice all these dents. A sol on Mars is a Martian day, 24 hours, 39 minutes. So after 402 Martian days, we've got some dents, not so bad. But after 477, Pete Teisinger calls me up to tell me we've got a hole in the wheel. That's not just a dent, that's a hole. And at this rate of degradation, we're going to be in trouble. So I got back to JPL, and then they showed me the really bad pictures, which, depending on your point of view, might be kind of cool. But these holes were made in the wheels, and they actually spell JPL in Morse code when we drive over the sand. Super geeky, but they had fun with it. This hole is not supposed to be there. That is not a good day on Mars. And so we got really worried about this. And so we stood down the mission. We didn't do anything that required any driving, and we studied it. And so, of course, the geologist said, well, that's because they're sharp rocks and we're driving over them. The engineer said, well, how many sharp rocks are there? And we're like, we don't know. Maybe there's an infinite number of them. So then this picture came back, And that's pretty definitive. So an engineer really likes something definitive. That's about as good as it gets. But it still has to be proven with an experiment.
2, 1, mark.
Okay. So here you go back to your basic physics class. What's happening in that picture is that we're driving the rover forward. And so when it goes over an obstacle, it has the static pressure of just gravity interacting with the wheel and the ground. But when the wheel goes forward, you're actually pushing it with a dynamic pressure. So that's why you can't take this wheelbarrow, and if you hit a curb here, you really got to bump it to get it to hop up. That's basically what just happened in that video. What we realized was if we drive the rover backwards, now we've got this situation. Everybody goes to the airport knows you just pull along, it hops up on the curb. So it all depends on where the pivot point is. So here's the experiment. Now we're driving backwards. Okay, so to this day we drive backwards. That was the engineer's contribution. So Pete goes off with the engineers, they dream up these experiments, and then what does science do? John goes off with the science team, and I look around the room, and I pick 6 or I can't remember. You can count the number of lines, that's how many people did this, except for the black line. And I pick that many scientists, and I say, okay, you guys get whatever data you want from orbit. I'm going to give you any data, any way you want it processed, whatever you get. You go away for a week, and you come back, and you find a better, safer route for us to drive in. This was amazing. This is such a great example of geologists in action when you have no guiding hypothesis. So what happened is, we were up here when the trouble started. The black route was basically the most efficient pathway we were supposed to be driving to get down to this site down here. Nobody agreed. So what you see is all these different range of possibilities. The green person said, I like what we had, it's the fastest and most efficient, just stick with it, let's go. The person over here says, I want this really long route that takes all of the highest hills because I think the tops of the hills are better. This person over here says, I want the really long route that stays in all the lows because sand accumulates in the lows, and that's the better route and we'll be safer. It may take longer, but we'll have less wheel damage. So the question is, what route gives us the less integrated wheel damage by the time we get here, no matter how long it takes? Suddenly time is not a commodity. Wheel damage is the commodity. That changes your... And then in between, you've got all these other ideas, and there was a big discussion about it. Guess what we did? Can anybody guess which route we took? Anybody voting for this one? Yeah, that won the day. So the logic was really good. The hypothesis, when the engineers got done the experiments, suddenly everybody's changing their bets to this one. You know, sharp rocks really are a bad thing. So we made maps, and this map, anything that's red looks like it's a real wheel problem. Anything that's blue or green looks better. And so we executed that route. The first thing we had to do was go through a gap right up here. That was the biggest problem with this whole route. We had to go through this gap. Can you tell how there's sort of a trough in here? We needed to be in that valley because that's where the sand is accumulating, but there's this big sand dune in the way. And we could see that sand dune from orbit, it was so big. So the problem is, you know, is it sort of out of the frying pan and into the fire if you take that route? You know, you got all these sharp rocks here, but if you get stuck in the sand, you still lose big time. So what we did was to study it. That's what you do. You don't want to just gun it and go because it's not really the Earth. And so here we did. We drove up. The first thing we wanted to do was to make sure that if we could cross over the sand dune, that there really was a good valley over here that had a lot of sand in it. And it does look pretty darn good. That was good. So you tick that one off, and now you get on with the most important question is this really sand? And all the geologists say to the engineers, of course it's sand. I can see all the grains. And they say, how do you know there's not foo-foo dust beneath it? You know, you're just going to drive up on it, you're going to sink right in, and you'll never get out. Well, sand dunes don't do that on Earth. Yeah, but this isn't Earth. And on and on and I go. Can you guarantee me? No, you can't. So what do? You do another experiment. So here we are doing the experiment. And again, there's a quiz show here. You can see if you can figure out what's supposed to be going on. We drive the rover up at an angle, so we get only one of the front wheels to go up on the crest, and it sits there. The other front wheel is slightly behind it, so if we do get embedded, we can hit the reverse and pull out of there. And so basically what's happening here, the only thing that's changing is the shadow. And so what we've done is to program the cameras to take a picture at more or less the same time of day. We drive up, wait the next day, take a picture, go to the next day, take a picture at exactly the same time so we have the same illumination, and then see if there's any sinkage. And so you can see these fractures that developed in the top of the sand. They're not getting any worse. That's a really good sign that we're not going to sink in. So that was the proof then that if we drive up onto this thing, we're not just going to sink into a pit of dust. So off we go, and we drive over it, and then we look back and we take a picture, and it worked. So what happened was we drove up over the crest. We command the vehicle because we know we're going to go down into a sand, and our worry is that if it is successful, we might run in and hit these rocks, which wouldn't be good. So we stop part of the way down, we do a wheel wiggle, and then we get information back to the rover that tells us just how slippery the sand is, and then we sort of slew off to the side, and then we avoid it. So that worked out really well. And that's sort of the end of my adventure. And now we've been driving ever since there. Our wheels are really torn up, but on the other hand, we accomplished everything we want to do. So I'll just finish this, so I do end it on a note of science. You know, you guys can all work on these missions. This sample return thing could go on for decades. And they need geologists, they need earth scientists, they need chemists, they need physicists. Anybody that's interested in this could potentially do this. And what this shows is a comparison of Earth and Mars. They are kind of similar, they're very different sizes. Their earliest histories seem very similar, and that's the reason to explore it. So I'll just finish with these two pictures. These are outcrops in the western part of Australia that are the oldest rocks on Earth that have any evidence of life in them. They're about 3.5 billion years old. But look, there's not that much rock here. It's not that well exposed. And this is a tiny, tiny fraction of the surface of the Earth. There's almost nothing left to look at. Here's Mars. These rocks are effectively the same age, and there's acres and acres and acres of them. So at a time when we know we had a biologic record on Earth, maybe Mars was doing the same thing. So there's a lot of rock left to look at here. The important thing is, because there was no plate tectonics on Mars, there's a lot of rock left to look at. And here's the best part. Even if life never originated on Mars, maybe you can go and find chemical precursors to the origin of life that were shut down for whatever reason that might have led to the development of amino acids and proteins and RNA on Earth. So you can sort of think of it as a chemical graveyard as well as a paleontological graveyard. Anyway, thanks for listening.
You want to answer a question or two?
Sure, I'll take
All
some
right.
questions.
Who would like to answer? Like, how could anybody not ask a question?
Yeah.
Ask a question.
So you spent a long time talking about this incredible landing procedure for landing a car-sized robot on a different planet. Within the last 2 years, there have been multiple nations who have tried to land smaller, less complicated rovers on the moon and have failed pretty spectacularly. Do you have an intuition for why NASA was able to pull off this $2.5 billion project without a hitch, and nations that are doing something where the communication time is significantly smaller have so much more trouble with our moon?
Yeah, there's a couple of answers. The first thing is NASA's been at it for a while now, and you start simpler and get more complicated. But I do think the big difference is that mantra, fly as you test as you fly. We just make no exception to that. And I didn't tell our darkest moment was when there were 39 motors on Curiosity. They were all made by the same vendor. They all have the same design. Initially, the motors were designed to use a dry lubricant, kind of a bismuth alloy. Think of graphite that you would use to lubricate something. The reason why is because if you use grease, you have to spend energy to heat that grease up because the viscosity of grease depends non-linearly on the temperature. So we wanted to conserve energy, so we went with the dry lube. Dry lube didn't work. First, we thought it was a badly manufactured unit when we did the lifetime testing. Then we thought it was actually the vendor. There was some kind of a manufacturing process in general that was weak. Then we realized it was our fault. And then we realized that we could not launch in 2009. So when you do that, and you have to go back and analyze and ask, what all do we need to do to be successful 2 years from now, it adds up to $300 million. And, you know, that was not a great day. You have to kind of crawl on your belly back to the guys with the money and say, give us another chance. But the reason to do that is to confess your sins, because if it works well in the end, those sins are forgiven. And I think that kind of integrity and the culture where you are willing to admit your mistakes in order to deliver something that works well is probably the biggest difference. Yeah.
Why do you care if the holes in the wheels? Holes isn't gonna hurt those wheels, is it?
Well, actually, what will happen is we've done the lifetime testing, and after a while, the wheel shears apart, and then you're just riding on the rim. And then after that, that breaks down. You know, it's funny. We were worried and we weren't, because in terms of the science, you know, that we had 2 issues in Science magazine. We did everything we wanted to do. The weird thing about it was, for a lot of people in the NASA family, they said, we built a vehicle to drive a minimum of 20 kilometers, and you've gone 500 meters. That doesn't feel successful. So there was a lot of stress that we should actually keep driving no matter what. The science team did want to keep driving. And you'd like to feel like you've delivered a mission that everybody feels successful with. So the concern was to study it so that we could figure out how to minimize the damage to lengthen the lifetime of the mission. That's the only reason. Yeah.
Did you say what the diameter of that parachute is at the bottom?
I didn't say, and I forgot. It's big. I think it's 60 meters.
How does it get packed?
What's that?
How does it get packed?
Oh my God, there's an incredible packing process. It takes about a week to pack that thing and to ensure that it's done it correctly. Yeah, and it goes into something that's half the size of a trash can. Yeah.
And you test that, I'm sure.
That's, yeah, so the squidding thing, so basically we go up to NASA Ames, which is in Moffett Field, just at the south end of San Francisco Bay, and that's the world's biggest wind tunnel, and that's where we did it. But the problem with that testing is it's not hypersonic, and so you have a good confidence, but not perfect. Yeah.
Are you changing anything about the wheels?
Thank you for asking that question. Yes, yeah, they're going to be much more robust. You know, these wheels, I mean, you know, again, this is a true story. You know, when I first got on the mission, I looked up at the Mars yard and I could hear this rover rolling along making all these pinging sounds. And I thought, what are these wheels made of? And I went over there and I went like this and it sounded cheap. And I asked the guys, and basically it's a 6-ply Coke can. Doesn't that sound bad? And so I said, this just seems like we're going to have trouble. And they said, oh, no, don't worry. You know, the gravitational constant on Mars is different. The problem was the rocks where we were a lot sharper. So the reason we have the mountain is because the wind blows so hard, it eroded all, the crater was once filled up. And the wind blew all the rock away. It eroded it all. So what it leaves behind are these things that look like pyramids everywhere. So it was kind of a lesson to everybody, and it's a reminder that Mars is a different place, and you can't plan for everything. But so this time they're much thicker wheels. They're going to work well. Yeah. Yeah.
Would you almost say that, like, the reason that you didn't keep driving with curiosity is because, like, now you understand all these things, like that's, it's almost like it's the test drive for the next one.
There is that legacy that we tried to build in, and so it's funny, the next mission to collect these rock samples, it's more sociological than technological now, because we know that vehicle is going to work. We're going to put better wheels on it and a few other changes, and it should work at least as well. And those guys, they have a command: thou shalt collect 20 to 25 samples minimum in a 2-year period. And so now the mission leadership has the challenge of, when we thought we found the promised land, we went 500 meters and drilled for a year and a half. Did science for a year and a half. Those guys can't just do that. They have to collect samples. They have to collect 20 samples, because the idea now is to sample the diversity of Mars. So you can't go back to the same thing that you think looks really good, because you don't know it's going to be good. So therefore you need to get this end member and that end member and this end member and that end member. So they have to keep driving and driving. So the challenge is going to be to figure out how good is, how much time it deserves, and then get going. That's going to be the hardest part of that mission. Yeah.
Are you gonna like explore the later chapters more in this mission, like the higher up hills?
In fact, the beginning chapters are even older than what we started with. So our rocks are probably starting at about 3.8. These rocks could start as old as 3.9, 4.0, and then there's a lake. Again, it's like a lake basin. So we're going to sample those older lake strata, and then we're going to drive up over the edge of the crater and get the really old rocks that are probably 4.1, 4.2, something like that. And so the emphasis is actually on the older rocks. Oh, here, right back here. Let's do that first, yeah. Oh, no, way back there.
I was wondering if you, how long the vehicle is going to keep on driving until the wheels
Till the wheels fall off. We hope that it will be coincident with the decline in energy. So the previous rover, like Opportunity, was built to last 3 months, and it went on for 12 years. And it was solar powered, and what we never expected to happen on Mars was the dust would accrete. What we didn't realize would happen is that come springtime, there's very high winds. They make dust devils. And they blew across and they cleaned off the rover every Martian year, which is every 2 Earth years. So this time we have nuclear power. We can measure it. Well, it's not nuclear power, it's nuclear powered. And then we collect electricity that we generate from the heat. And so we can measure the decline of that heat and see very accurately how it's declining. And we can also see kind of how our wheels are declining. And I would guess that 2 or 3 years from now, it's not going to be able to do much. We'll probably be able to drive once a week instead of once every day. We'll have to choose our targets very carefully, because we'll be there having to power up again while we store energy and do measurements. So it'll get slow in about 2 to 3 years. And then here.
So has the rover been affected by any storms or anything?
No, Gale Crater seems to be a pretty mellow place. There have been these global windstorms. There was the biggest one ever, and that's probably what killed off Opportunity in the end. We could see the energy diminishing as the dust accumulated as the storm intensified. But it doesn't make any difference for our rover. What we were more worried about was that the dust would accumulate on the rover and cause thermal blanketing, keeping the heat in and changing the properties of the rover. So, but everything seems stable. Yeah. David, we'll get to you.
You should take everybody else.
Yeah, here's one.
Sorry, it's another wheel question.
Yeah. Oh, I like wheel questions.
When you were phrasing your answer previously, you mentioned it was something like a 6-ply Coke can. I assume that means it's made of aluminum.
Yep.
Are there other metals that might work better, or different materials that might have more give that would be better suited to it, or is this like a series of intense testing that led to aluminum?
It was a very deliberate choice. You could have gone with titanium, which would have weighed a little bit more and been a lot stronger, but the manufacturing, the way that the wheel is made, each wheel costs about $60,000. And the reason why is it's milled from a single piece of aluminum. Yeah, maybe someday they'll 3D print them, but not now. And so you don't want to weld it, because every time you have a weld, you have a potential zone of weakness. So it's basically lathe from a single block, and aluminum is the best material for that. If you make it thick enough, it's just fine for the job. Ours were just a bit thin. Yeah, yeah. David, go for it.
You talked a little bit about the new landing site for Mars 2020, Jezero Crater, and mentioned that there's this, like, hopefully looking, what were some of the reasons that there was a long process of choosing the new site? What were some of the qualities of this site that made it, in the end, the choice?
Let me go back. This one picture will sort of say it all. Yeah, so the 2020 rover is going to go to a site that looks exactly like this. It'll land out here and then drive over towards a delta. But the answer that I had to your question is, unlike this delta, which is thought to be on the order of 3.5 to 3.2 billion years, this place that 2020 is going to, that delta is maybe 500 million years older. So the notion is that the older you get on Mars, the more water there will have been, maybe life is better preserved. And so the reason you want to go to a delta is that at the bottom of the delta is where all the clays occur, and clay is a great material, at least on Earth, to preserve microorganisms in. So the idea, out of all the landing sites that were available, this was the only one that had a really old delta. And so that was the number one pick for all the astrobiologists. However, this is not just, it's supposed to be a sample return mission. So what they're hoping to do is to sample the base of the delta and then drive up and get into the rocks that are outside of the delta, which are the ones that are really old, and then look for fractures that are filled in with minerals that formed in water. Because some people, some microbiologists, terrestrial microbiologists, have demonstrated that microbes can live quite deep in the earth, in the crust. And so the thought is that maybe that's where life originated on Mars, or maybe it once lived and is preserved there. So the notion is to sample both environments, and that's why that site won the day, because it had a little bit of everything. And that's kind of what happened with Gale, too. A little bit of everything. Yeah.
So with all the hype around human missions to Mars,
Oh.
is that pulling funding away, or is it helping you make your case, rightly or wrongly, for whether that should happen? Is it helping attract interest to future Mars missions? How's the politics playing out for the funding?
No, it never changes. You know, if you want to do humans, you just do humans. You don't need to go to Mars. You don't need to go to the moons. Let's just get on with it. But the problem is it's so expensive. There's chest beating that says, you know, we're going to do humans, but then there's no budget for it. So I think a historian will come back and look at the legacy of NASA. You know, if you came back sort of 20 or 30 years from now and look at it, you'll just see a steady decline in funding. And who knows what Bezos and Musk and these guys are going to do and how that will or won't replace what NASA's doing. But the bottom line is that actually the president's budget had a slight increase for space science. Whatever you think about that, that's the reality of it. But it won't amount to anything substantial. So I think we're kind of getting down to a flatline situation, and you know what happens after that is anybody's guess. I don't think it's going to increase, though, because I think that the robotics and this kind of technology, and that you could have a private company launch a mission that's small, efficient, and fling a nanobot out there. Who knows what a nanobot could do in 20 years. So it could be that there's just economies of scale that somehow you can produce, instead of doing one of these things every 10 years for $2.5 billion, maybe you can do hundreds for 10 million. Yeah.
You talked about how the next rover is sort of going to be more of a copy of the current generation than that. I guess my question is more, if you could design your dream rover and you didn't have to really worry about that, what would that look like? Would it be a copy of Curiosity? Would
Nope.
you want to add any stuff?
Thank you. That's one of my favorite questions. You know, I can't complain about the flagship mission that I worked on. It was very successful. I do think it was a great use of funds. The problem is it's forcing us as scientists to overpredict and be more confident than we can be about where the good stuff is. If you take the view that we don't really know what we're talking about, that you're much better off to build things that are a little less capable, that will allow you to survey a broader range of terrains on Mars. The reason why the science community has such a difficult time on agreeing what the final landing site will be, because there are so many good ideas, very few of them are constrained by robust observations that allow you to objectively say this one is better or worse than the other one. So I would prefer to do what I call boutique missions, where you build something for a couple $100 million and you send it to this place to make that measurement based on a hypothesis that you develop from orbit. And then you take the same platform and you put a different instrument on it and send it to that place and make a different measurement based on the hypothesis that you think makes that place special. And I feel like that's a better way to go about doing exploration than it is to put all your eggs in one basket and hope that you got the right place. Because, I mean, look, if you go back and you look at the history of discovery of life on Earth, you've got Darwin, who everybody thinks did the beagle and did finches and all that, but Darwin also wrote about the fossil record, and he said, if my idea is correct, then beneath the trilobites, it's such an advanced life form, there should be, they just haven't been discovered yet. He called it the Pullian interval. How long did it take till we found those other life forms? 100 years. And it was an economic geologist that in 1950 found the first microorganisms in southern Canada. It was all luck. People had been looking at those kinds of rocks for decades with exactly the same technology, the same kind of microscopes. And so the lesson about Earth is that the Earth is teeming with life, but it almost never gets preserved. That's why fossils are cool. So if you take the same approach to Mars, I mean, what's the likelihood that we're going to come back with 2020 and find fossil microbes even if life did originate on Mars? I think the chances are small. So then what happens? Congress says, you guys have had enough. You did this before, you did it again, you didn't find anything, we're going to do something else with the money. And so I think we're better off to be a little more circumspect and say that, we don't really know, but we should sample diversity and build more missions at a cheaper price. NASA does do a little bit of that, but I don't think they do enough. Yeah.
Is there a secondary mission to Mars 2020, or is it simply just to look for fossils in the fossil record?
No, it's supposed to be, nominally the mission definition is it's sampling the diversity of Mars. But the reality is that the money is appropriated by Congress to do the astrobiology question. So what we try to do is bootleg and build around that opportunities that fold in answers to other problems that are extant as well. Yeah.
It seems that all of the missions you've discussed today are focused on information that can be found from the rocks of Mars. Is there discussion around sending missions to the polar ice caps?
Oh, yes, there is, but we can't go because of planetary protection. So unfortunately, there's nothing equivalent to the Antarctic Treaty where all nations agree to do this and that and not do this and that. Mars is up for grabs, whoever gets to the poles first, but the U.S. has a commitment to not trying to do forward contamination. So the problem is it's the uncertainty that you could put something. There's a cool mission I like, it's called Cryo Bot. You land on the pole and this thing melts its way through the ice sheets down to what could be a lake, just like Vostok, where who knows what's down there. But the problem is to get it clean enough, you have to sort of eliminate all microbial contamination, and nobody thinks they can do that. And if they do, it costs so much money that when the science community votes for missions every decade, it's called a decadal survey, it always falls, not to the bottom, but just it's not at the top. So, people are looking at other places like moons of Jupiter. Europa is a very attractive spot to go to explore ice, and there they're going to have to come to grips with that. Yeah.
Sorry, I have another question. Have any of the rovers on Mars been affected by solar activity or solar events?
Yeah.
How do you deal with that kind of thing?
That's also what takes out other spacecraft that other countries launch, often it happens while they're going to Mars. They get hit with a big solar wind, and the components of the central processing unit, especially the chips, the microprocessors, are not radiation hardened, and they get zapped. So NASA is almost like a troglodyte that way. They will not use, and our computer is your phone is much better than our rover computer. And so they tend to it still uses the Wind River operating system. So they tend to use the same hardware that has been proven over and over again in testing and in flight. So you know, that's probably how that's going to keep going.
All right, everybody. We are very grateful that you came to give your attention to this. Give one more round of applause.